So, question, you want to go back to that designated, like, I think it's. Oh, wait, if I said that. There's something. So only one person can say. And then you just have to be able to track when everybody has gotten the opportunity to track. So. I think everyone is allowed to mark them out. Because then what if they get the reback? If they get the reback, then like just. Yeah. They can't get. Then they leave it. If anybody can revoke, and so that. Like I'll live at the light. Blood in my body. I think she does. Somehow that first person. The first person. That just goes back to the. No, I'm just saying what the solution gave you. I'm gonna tell you. Okay, no, the advice I was giving is.
Okay, so page 14. We're going to talk about 3 convergence tests today. So I want to introduce these two. We'll definitely have time to review through these, but we're going to try to get through 3 different tests today. So let's say we had rule of sequence A sub n, and we were able to add all the terms in the sequence, so A sub 1 plus A sub 2 plus A sub 3. And if our series converges, then our rule of expression itself, it has to get smaller, right? So that's the idea, is that if my series is going to converge, then each term basically has to get closer and closer towards 0. Basically, it has to get smaller, right, towards 0. However, the opposite may not be true if my sequence is if the terms of my sequence is getting smaller, it still may not be enough, meaning that my series, it may converge, but it could also diverge. So just because my terms are getting smaller or my term sequence is getting towards 0, it doesn't guarantee that my series will converge. So we have this nth term for divergence, which says that if the terms of my sequence is not getting towards 0 or getting closer towards 0, then I can absolutely say for certain that the series will diverge. But if the limit of A sub n approaches 0, then all we know is that it will have a chance to converge, but some additional tests will have to be used to confirm that it does diverge or converge. So this nth term for divergence is only a one-way test. Okay, if we can show that the rule of sequence doesn't get closer to 0, we can just stop the problem and say that the series diverges. But if the limit does approach 0, then all we can say is, okay, it's inconclusive. We may have to dig a little deeper. So even though this is not a two-way test, this is still a very useful test because this is a quick one to use, a quick one to get through. And if we can quickly show that a series will diverge, it will save us some time. We don't have to go through a whole, complicated rule if we can already show that the a sub n as n approaches infinity doesn't equal to 0. So I like to have this as a first test for any test where it's not obvious what test it is. I like to just do a quick divergence test or nth term test just to get it out of the way, because if I can, that way we don't have to spend a whole lot of time on something that can be solved, that can be determined within, 30 seconds. Okay, so let's look at number 1 here. It says use the nth term test to make a conclusion about the divergence for each series. So here we have a rational function, and rather than looking at other tests, we choose nth term test. So nth term test just says, okay, I'm just going to look at the rule of sequence. Okay, is my rule of sequence approaching 0? So here, what is this approaching? This function, 3/5, right? So if my term is getting closer towards 3/5, that means it's not getting closer towards 0. If it's not getting closer towards 0, there's no chance that adding all these terms up will get me to a converging series, because it's not getting small enough for us to get there. Okay, number 2, use the nth term test. So another way to write this is 3/2 to the n. Can we say about the rule of sequence here? It is approaching 0, right? So by the nth term test, we would say it could converge, but this is inconclusive by the nth term test. Now, in reality, we would just look at this and realize it's a geometric series test. We wouldn't go through a full nth term test. So, there are some series where you can instantly tell what category falls under, and you don't have to go through the nth term test. I think nth term test is more, okay, it's not obvious what category falls under. Let me just do nth term test just to kind of get that out of the way. But we do know that this converges because this is a geometric series test. The ratio is less than 1. So we do know ultimately the series converge by geometric series test. I'm going to abbreviate geometric series test with GST, because R is equal to 1/2, which is less than 1. So we did practice through going through nth term tests, but ultimately that's not what you're going to do, which is fine. Because it's easy enough for us to determine. Okay, next up. Our series is 1/n as n approaches infinity. So we're just going to put limit as n approaches. We're going to look at the rule of sequence and see, does the sequence head towards 0? And what can we say here?
Yes,
it does go towards 0. What can we say about that? Inconclusive, that's right. So this is by the nth term test. The convergence is inconclusive. So this could converge, it could diverge, and this is something that we're going to talk about on later today, called the P-series test. This looks like it should converge because it's getting smaller, it's headed towards 0. But this is actually going to be one where it's right at that line where it's not quite getting smaller fast enough where it does diverge. But we'll talk about this a little bit later. Okay, number 4. We want to find the limit as n approaches to infinity, but maybe it's best if we can kind of split things up and helps us see things a little bit more clearly. I'm going to separate the numerator and denominator just so I can have an easier time kind of picking apart what's really happening. So here we can tell that both the numerator and denominator are growing at the same rate because they both are growing at the exponential of 2 to the n. So basically, we just look at the coefficients, right? And the limit of this rule of sequence is what? Is 1/2, right? Which, what can we conclude? It's not equal to 0. So it's not, if my rule of sequence is not headed towards 0, there's no chance that I can add up all the terms to infinity and get it to head towards a number, right? That the ceiling is going to be unbounded. So diverges. So this is a good one where the nth term test does actually give us a quick conclusion without having us to resort to any more complicated convergence rule.
The function grows faster than the.
That's right. Yep. So let me review growth rates here. So if we're doing limit as n approaches infinity of a function, and we're dealing with different functions here, your log function is going to grow the slowest, followed by your radical, followed by your polynomial, and then followed by your exponential. So I have an exponential over algebraic or polynomial. And it's obvious that the numerator is growing faster than the denominator, so therefore this is headed towards infinity. Obviously, it's not getting smaller, so this is a good one for us to say also diverges by nth term test. Okay, we'll try to get more practice in, but let me talk about the second test, and that's the integral test. I'm going to skip the graph there to show. I don't think it's going to be that important for us to. I think the important thing is just for us to know that the rule for integral tests, which is copy down the rule here. So this says that if a function is positive, continuous, and decreasing, meaning that that this function has to be above the x-axis. It has to be continuous. They can't have any asymptotes or holes. Now, this continuous, it just means that there could be an asymptote, but then once we start to the right of that asymptote, it needs to be continuous. Okay, so wherever the graph starts, it could have an asymptote at 1, and then the graph starts to pick up at 2. Then as long as it's continuous from 2 on, then we can have it pass the integral test or pass the condition, and it's got to be decreasing. Right? So then if I can show that the series, I can show the series converge by taking the definite integral or the improper integral. So if the improper integral can give me a number, then I know that the series also converges. If my improper integral goes to infinity, then I can say that my series diverges. However, we can't, if this converges, we can't say that, oh, this converges to, the integral goes to 3/4, so therefore the series is 3/4. That doesn't quite line up. Right? So if we get a real number, that doesn't necessarily mean that is the sum of the series. It just means that it's a condition for us to know that it converges. So we're going to go through the integral test. This is an important test. However, this is going to, as we go through a series of tests, this is going to be one of the last one that we want to test. This because it takes so long. We prefer to go through our other options first before we commit to integral test, because it's just a little a little time consuming. So it's almost like a last resort. It's like, oh, okay, if I can't get nth term to show me what I need to see, and it looks like something that use substitution can handle, okay, fine, I'll do we'll do integral test. But typically, we like to cycle through the tests that are quicker before we commit to integral test. Okay, let's skip the graph and let's look at number 1. All right, so number 1, we have 1 over n ln of n. If we do n, so if I see this, typically we will say, okay, let's do nth term test. And nth term test will tell us what? The limit of this would equal to what?
1 over 2 that belongs to. Zero.
Yeah. So we know that nth term test would be what? Inconclusive, right? So we wish that nth term test would be able to get this to something conclusive, but it doesn't. So now we're looking at a problem that it looks like maybe something that use substitution can handle. So it looks like this could be a good fit for integral test. But there's 3 conditions we have to make sure that we pass. So we have to make sure we state those conditions. So. So in order for us to even use the test, we need to make sure it passes the condition. So the condition has no say as to whether it converges or diverges. It just tells us whether we can use the test or not. Okay, so we don't have to show any proof for it. We just have to kind of list it out. Let's check conditions. And I can say the function is positive. Right. Any value past 2, it's going to be a positive number. And it is continuous. There is a vertical asymptote at 0, but it's not going to affect because we're starting at 2. So once we get past 2, there's not going to be any breaks in the graph. And we can tell that it's decreasing. That's not going to happen. Yeah. The problems that you get on the assessments as well as the AP exam, if they ask you for conversions, there will be something that I conclude with. It won't be something that we have no way of getting to, right? So one of the tests will work if it's given to you on the test. All right, so and it's decreasing because, well, we tried going through nth term test and it is decreasing because it's headed towards 0. So this is a good candidate for integral test. So we're going to go through our steps here. So we're going to do limit as n approaches infinity from 2 to infinity, but we're going to let b hold that that infinity value. And we'll get this in terms of x. It just feels easier for us from a calculus perspective. Okay, so now this, we'll go through what we did with improper integrals before. We gotta go through substitution, right? What could be our u value? So we'll go through the whole step here.
Should that be the n, like on the bounds?
Mm.
It says the limit as n plus infinity.
Oh, sorry, my bad. Yeah, b, my bad. B equals. Okay, so u equals natural log of x. X's cancel out. We have a rule, which is natural log. So natural log absolute value of u, which is natural log of x. Okay. We have our antiderivative. We can now plug in our upper and lower bounds. Okay, so if I insert infinity in for b, what's going to happen here? Well, this, yeah, it'll keep going to infinity, right? So we know this is infinity here. So we know that because the integral diverges, we can therefore backtrack and conclude that the series, this series must diverge as well. So we can say the series diverge by integral test. Okay, number two, even though it's asking for us to do the integral test, I like to just always get into the habit of let's do a quick nth term test, right? That's just I like to have us build that habit so that because it only takes a few seconds, right? Let's just get that out of the way, and then we can always be doing that unless it's obvious what rule you want to, unless you can just instantly tell what rule that you want to use. I like to have us practice nth term test. So here, nth term test, what? Inconclusive, right? It does go to 0. But it's also nice for integral tests because we know that, okay, it's decreasing. So that is a condition that we need. Okay. So we can say that the series is positive. And it looks like this is one that integral could do, right? We can do power rule for this. And so we can definitely take the integral of that. Let's just list out our condition though. Series is positive, continuous. I mean, there is an asymptote, but as soon as we start at 1, we're not going to experience anything, right? We're going to be fine, and it's decreasing. Okay, this is not a natural log, right? This is x squared in the denominator, so go through power rule. Okay, so if I insert infinity in for b, what's going to happen here? 0. 0 plus 1/2. I'm sorry, 0 plus 1. No, sorry, it's and 1, not 2. Zero plus 1 is 1. This is a real number, so we know that the integral converges. Therefore, the series converge. Again, this 1 doesn't mean anything from a sum standpoint. We can't say that the sum is equal to 1. All we can say that is, okay, that's a real number. Series converges by integral test. Okay, there's an even better test for this, and we're gonna talk about that right now. But this is also, like after we learn the new one, we're never gonna do integral test for something that looks like this. But this is always a good candidate, something that doesn't fit into other tests, and nth term test doesn't work. We're kind of forced into integral test for something that looks like that. That looks like a U substitution probably. Okay, next up, P series. So P series is let P be a positive constant of the series in the form of 1 over n to the P. So n is going to be your variable. So you have a variable raised to a constant, a given constant. Right. Now we ought to make sure that our P value is positive in the denominator in order for us to do this test. Okay. So if our P value is positive in the denominator, then we can say that as long as the P value is greater than 1, the series will converge because this series is going to get small fast enough where we can guarantee that it converges. But it will diverge if the P value is between 0 and 1. The reason why they say P value is positive in the denominator, because if it's negative in the denominator, then we should really bring it up and go through nth term test. There's no need to go through P series test if it doesn't fall into those categories. So we talked about this series, this 1 over n. We looked at it before, where we saw that nth term test was inconclusive. So now we know that this is a very special case of the P series test. This is called a harmonic series. If the P value is 1, you just know that this will diverge. Okay. So this is a special case here. Not special case in the sense that, I mean, it does fall under this diverging, but we are going to see this quite a bit. And if we can recognize the harmonic series, we'll just know instantly that it diverges by the P series test. Okay, let's look at number 1. Do the following series converge or diverge? I have 1 over n cubed. Okay, looks like this falls nicely into that P series. I have a variable raised to a constant. My P value is what? 3. 3 is greater than 1. Therefore, what? Converges. Here, I have 1 over square root of n. I can rewrite that square root of n as what? 1/2. My P value is 1/2. It's less than 1, therefore diverges. Thank you. Yes, every day. It's amazing. Okay, any questions so far? We'll just do the non-AP problems. Okay, I do want to point something out here about this is I want to make sure that we don't get P-series and geometric series confused because they can kind of look the same or look similar. Remember, geometric series is if I have a constant raised to the variable, right? That's my R to the n. But a P-series is if I have a variable raised to a constant. So just make sure that we don't confuse one for the other. Okay, let's look at number 3 here. Number 3 says, for what values of k will the series converge? Okay. So we want to basically fit into this mold of 1 over n to the p. So we know what the condition is, right? My p-value has to be what if my series is going to converge greater than 1. So let's just set up that inequality, right? We know that 2k minus 5 must be greater than 1 if my series is going to converge. Because that exponent represents my p-value. So I can just go through this inequality and just solve for k, and whatever the inequality gives us, then those are all the k values that will allow p to be greater than 1. Okay, next up, I want to get it into that form of 1 over n to the p, and I can merge this together, make this what, n to the, yeah. So as long as 2k plus 1 is greater than 1, we know that it will fulfill the condition of the series conversion. Okay, for number 5, this looks a little bit different here because doesn't quite fit into that 1 over n to the p as well. But what we can do is we basically want a 1 in the numerator. So what can I do to all 3 terms here to get a 1 in the numerator? Divide by n, right? So, or multiply by 1 over n. Okay, we know that 5 over n will just go to 0. So really, we can just focus on this piece here. I can rewrite this as n to the 4k minus 1. Just focus on this here, right? So 4k minus 1 has to be greater than 1. Okay, let's see if we can make some progress here. So our strategy for this is we should always do nth term unless we can clearly recognize that it's a rule that that we can go to without any issue, right? So if it's obviously a P series, if it's obviously a geometric series, we can maybe not go through nth term. But if something doesn't quite fit a geometric series or P series where it's obvious what category it is, we should always do nth term first. So look at number 1 here. Nth term looks like this could be a good candidate for that one. What does nth term tell us?
Divergence.
Divergence, right? Because the limit as n approaches infinity of this is going to be compared to degrees. Degrees are the same. We get -2/5. -2/5 is not 0. If my term is, each term is not getting closer towards 0, I know that this series has no way of converging. Number 2, we could do nth term tests, but can we tell what that is looking like? Looks like what? Yeah, looks like geometric series, right? We can rearrange it to get it into geometric series form, and we should be able to not only get to whether it's converging or diverging, we can also find the sum as well. It's not asking for the sum in this case, but well, let's just get the habit of looking for the sum, especially if it's geometric series. So if I rearrange this, I can definitely make this into my ratio being 3/5. If my ratio is 3/5, that's going to be less than 1. So my sum is a sub 1 over 1 minus r. Number 3 looks like it doesn't fit into a test that we know that we can easily categorize. So nth term would be good for that. What does nth term tell us for number 3? Divergence, right? It doesn't equal to 0. So if it doesn't equal to 0, that's enough for us to say it diverges.
You find the limit there, like when it's under the radical.
Right. So what's square root of n squared? That's basically n to what power? 1 n to the first power. So basically degrees match. So if I clean that up, isn't it the same thing as that? You know, so. Okay, what does number 4 look like? Yeah, it looks like it's geometric, right? E is less than pi, so know that our ratio is less than 1. For number 5, normally, maybe that would be a good fit for geometric series, but that +1, that is not in the exponent. It kind of throws things off a little bit. It doesn't quite fit into, we can't quite rearrange it into geometric series. So let's do that term instead. So if I split that up into 2 fractions and look at the limit individually, the first one will give me 1/7. The second one will give me 0. 1/7 plus 0 is still not 0, still greater than 1. It'll still diverge by nth term.
You split it into like 1/7 times. 1 and then, if one of them diverges, can you say like the whole thing diverges?
Yes, right. Yeah, because we know, right. We don't even have to look at this one here. Like, once we know that this doesn't go to 0, we know that the other term doesn't matter what's happening to it. Number 6 should be easy for us to spot, right? That it's already in that geometric series form. My ratio is greater than 1. I can just quickly say that my series diverges by geometric series test. You can also say nth term test for this and say it diverges, but either one's fine.
Pardon the interruption. This is an announcement for rising 10th through 12th grade students. Today, in advisement, you will receive a pink course verification form. This form is a combination of the courses that were recommended for you by your teachers and the electives you requested last week. If you would like to make any changes to the courses on your form, you will cross off the courses that you do not want and write in the courses that you do want. If you want to take an online course next year, you must complete the attached online course contract with a parent signature. If you want to waive into an honors or AP course, you must complete the attached honors and AP waiver. There's a back to the form with a parent signature. If you are a rising 10th or 12th grader and you do not receive your form during advisement, visit your assigned counselor between classes today to have a new one printed for you. Students with questions or concerns about their form should visit counselors in the media center tomorrow, Wednesday, between 8:20 and 3:30 in lieu of booking an appointment. All forms are due by 3:30 p.m. on Wednesday, February 14th. This is for teachers. If you have a current 9th through 11th grade advisement class, please do not forget to distribute your forms in advisement today. If you have students who are missing a form, direct them to visit their assigned counselor between classes to have a new one printed. Please do not send students to the counseling suite during advisement or during instruction time unless they have a scheduled appointment. Thank you so much.
Okay, so your homework tonight is 17 to 24. We'll push that AP practice till weekend homework for 10.4, so it's 17 to 24. No AP practice due tomorrow. Okay, all right, go get your phones. There's no first time.
I mean, you just go up there and have to go like. Probably not confident. But now you gotta have a designated server. And you gotta tell everyone, like, it's gotta have something to do with like.